Okay, so in this video we are continuing with limits, and in this one we're just going to go over some properties as well as rules of limits. Okay, so properties and rules of limits. Okay, so let's just jump into it, and we're going to talk about some scenarios and limits that will come up really often, and we need to know how to quickly kind of deal with them. And that first scenario that we get is going to be the limit as x approaches some number a of some constant. Okay, so the limit as x approaches a of some constant. Okay, and I can just give you the answer here, but it's better that you kind of see it for yourself. Okay, so what is the limit as x approaches a of some constant? Well, let's draw a graph. Okay, let's draw a graph, and all that graph is going to be is it's going to be the graph of our function f of x. In this case, that function is just a constant. So what does a graph of just a constant equal? For example, y equals 3, y equals 2, y equals 0, y equals negative 1.37. What does that look like? Well, if we want to graph the function, it's just going to be a straight horizontal line. That is our function f of x equals some constant c. Okay? And now we ask ourselves, what is the limit as x approaches some random number a? Let's pick this number to be a. Okay? As we approach a from either the left or the right, we are going to get to some sort of a value. Well, what is that value equal to? What is the y value equal to? Well, it's just equal to that constant. And if I move my a, let's say over here, again, as I'm approaching it, both from the left and from the right, first of all, I can see I'm going to get the same value. Okay, so our limit from the left and from the right is equivalent, so the general limit does exist. You'll remember that from last video. And the second thing is, well, again, what is the y value of it? Well, it's just whatever value this constant is. And I can move this a anywhere I want, but I'm going to get the same thing. First of all, I'm going to get that the limit does exist. Second of all, I'm going to get that the value of that limit is just the value of the constant, because this line doesn't have a changing slope. Okay? And if it doesn't have a changing slope, well, it's just this constant. So this limit, the limit as x approaches a of some function that is just a constant, the answer is that limit is that constant. So for example, the limit as x approaches negative 1 of the function 3 is equal to 3, right? Because again, if I were to draw my graph, this function f of x equals c, well, now it's just f of x equals 3, and now instead of my a being any sort of a, it's this a right here, let's say, negative 1. And, well, what do I get here? I get this value. What is the value here? Well, the value is 3. Okay? And this works for anything. I can say, what is the limit as x approaches pi divided by 3, and then we take the whole square root of it, of some function negative 1 over 5, let's say, just like random numbers. What is this limit equal to? Well, it's just equal to negative 1 over 5. Okay, so that's our first kind of a property, or more so our rule. And the second one that that I'm going to mention here is, what is the limit as x approaches a of some function, and that function is going to be the function y equals x. Okay, what is this limit equal to? Well, again, we can draw a graph and kind of see for ourselves what we expect. So if we draw the graph of y equals x, what is it going to look like? Okay, well, it's going to look like a line. It's going to be a straight line that goes through the origin. Okay, and it's going to go over 1, up 1, over 1, up 1, over 1, up 1, over 1, up 1, so on and so forth forever, or the other way down if you're going to the left. And so I ask myself, well, okay, let's pick an arbitrary random number. Let's do a. Okay, and I go up here. This is where it is. What is the y value this. Okay, what is the y value? Well, the y value is also happens to be a, because this function is y equals x. When x is equal to 10, y is equal to 10. When x is equal to 0, y is equal to 0. When x is equal to -3, y is equal to -3. Okay, so no matter what x value we choose, the y value is going to be the exact same. And so in this case, we can say that the limit as x approaches any number a of the function x, the limit of that is just the value of a. Okay, so if I ask you, what is the limit as x approaches -3 of the function x, your answer is going to be -3. And if I ask you, what is the limit as x approaches negative 1965.2 of the function x, well, that limit is just negative 1965.2. Okay, so these are our two rules for limits. The limit of a constant is equal to that constant, and the limit of the function x is equal to whatever that limit is approaching, whatever x value, whatever value x is approaching. Okay, and then kind of a third sort of rule that I will quickly just mention. We discovered this in the previous video. So number 3, I suppose, is just the limit as x approaches 0 of the function 1 over x. And we saw this in the other video. And in this case, this limit is just equal to, sorry, not 0, definitely not 0. It does not exist. However, the limit as x approaches 0 from the left-hand side of 1 over x is equal to -infinity, and the limit as x approaches 0 from the right-hand side of 1 over x is +infinity. Okay, so this was from the previous video. If you missed it, just go check that out and you'll figure that out yourself. Okay, so those are kind of 3 of our basic rules for limits, and 3 of the rules that we are going to use to really help us solve limits. Okay, and now we've gone through some rules or some basic limits here. Let's quickly go over the properties of limits. Okay, so properties. So quickly, there's 4 different properties that I can think of that are really important. The first one being the limit as x approaches, again, some number a, of some function f of x added or subtracted from some function g of x. Okay, so for example, f of x can be like 3x, and g of x can be like 2. That is, after all, a function of x. Okay, so if we have 3x plus 2 or 3x minus 2, okay, what can we do with that? Well, what we can do with it, our properties, say that we can actually split that up, and we can split that up as the limit as x approaches a of f of x plus minus the limit as x approaches a of g of x. Okay, so we're allowed to split these functions up. Okay, and if you're a little bit confused by this at the moment, it's all good, don't worry about it. We're going to go over examples where we actually apply these rules or these properties in order to simplify expressions and be able to solve them. So we will see real life actual examples of this as well. Okay, so that's our first property. The second property, going along with the theme of addition and subtraction, we're going to move on to multiplication and division. So the limit as x approaches a of, again, some function f of x, in this case multiplied by g of x. And again, just like with addition and subtraction, we could split up the one singular limit into 2 different limits. We can do the same thing here. So this is just going to be the limit as x approaches a of, of f of x multiplied by the limit as x approaches a of g of x. Okay, and then similarly, the limit as x approaches a of some function f of x divided by some function g of x, as you can imagine, this is equal to the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. Okay, and then there's one more here that I quickly want to mention, our last one, the limit as x approaches a of some function f of x. In this case, we don't need g of x, we just need one function f of x. Okay, f of x to some exponent, okay, raised to some exponent n. This is equivalent to the limit as x approaches a of f of x, but this whole limit is now, okay, is now, that power is now applied to this entire limit. And this one may be a little bit more difficult to understand or to visualize, but for example, if I have the limit as x approaches, let's just give a random number, 1, of some function f of x, let's say that function is the square root of, let's just say x, doesn't matter, so this can be rewritten as the limit as x approaches 1 of, remember, square roots you can write as to the exponent of 1 over 2. So this is going to be x to the exponent 1 over 2. And we can rewrite that as the limit as x approaches 1 of x, and then this whole thing is raised to the exponent 1 over 2. And remember, we know what the limit as x approaches, the limit as x approaches any number of the function x, we know what that limit is. So actually we can answer this right now if we want. If we go back up here, we know that the limit as x approaches a of some number x, of some function x, is equal to just a, or is equal to that number. So this limit is just equal to 1. So this is just equal to 1 raised to the exponent 1/2, or just the square root of 1. The square root of 1 is just 1. And so this limit is equal to 1. Okay? So that is kind of why we want to apply these rules, because we don't know what the limit of the limit as x approaches 1 of x to the exponent 1/2 is. But we do know what the limit as x approaches 1 of x is. That's one of our rules that we just discussed. And so we can answer this bottom limit right here, but we cannot answer this limit because we don't know what the limit is of x to the exponent 1/2, but we do know the limit of just x. Okay, so that is kind of the reason why we would want to use these rules to help answer these questions. Okay, so that's everything for this one. The only other thing I wanted to mention is here with our limit, with our division limit, the only exception is that the limit as x approaches a of g of x, so of the denominator, it cannot equal 0. This should be fairly self-explanatory, but it is an important kind of exception, just to write it down. This should be fairly self-explanatory because, again, we can't have a 0 in the denominator. We're not allowed to do that. So just kind of keep that in mind. But other than that, there's no exceptions to any of these rules. Okay, so that's everything for this video. In the next one, we're going to be using these properties as well as our knowledge of the limit of a constant and the limit of the function x. We're going to use those to help solve actually any polynomial limit that we get. Okay, so that's coming up in the next video.